Good morning or good afternoon, and welcome to Physics of the Universe. This is part 4 of the video series I've been doing about weather. Today is going to be about methods of heat transfer. A lot of this actually is going to be stuff that you probably already know, but we're going to give it some terminology, and then the next unit we'll actually get into what exactly causes that, how it affects the weather. So let's get on with it. Heat, as you guys know, is it's a form of energy. We call that thermal energy. We talked about that in class before the hiatus. It's basically defined as the amount of total kinetic energy that all the atoms have that make up a substance. The temperature of an object, and we talked about this at the beginning of the year. Remember, there's no such thing as cold. It's just how much heat is in the object or how much heat is not in that object. That's the whole Kelvin scale was based on the idea that every object has some sort of heat in it. You can take an iceberg. If you take an ice cube out of your refrigerator, ask yourself, can you get it colder? And if you're going to get it colder, how are you going to get it colder? Well, you have to take energy out of it. You're going to have to remove that heat energy. So even an ice cube from your refrigerator has heat inside of it. You can always get it colder. When we're talking about heat and heat energy, really what we're talking about is not, strangely enough, it's not how much heat is giving off, it's how much the atoms inside of that object are vibrating. And if you take a look right here where it says solid, with a solid, the atoms are not vibrating a lot. They're vibrating a little bit, but not so much that they are separated from each other. So when you have something that's a solid, it's pretty much hard. You can kind of knock on it, and the atoms are going to stay kind of bonded to each other. When we get to the liquid state, what's happening with the liquid state is that the water, or in this case, Pepsi, there's enough heat in that object to where the atoms are vibrating so much that they slide by each other. But gravity is still holding it down, and so kind of holding them close together. When we get to gas, because I just shook this up, what's going to happen is I'm going to release this, and it's going to release gas. What's happening is that the gas has gotten so warm inside of that container that they started bouncing off of the side of the container. They're vibrating so much, they're bouncing off of each other, they're bouncing off the side of the container, and they're expanding. And the hotter you get it, the more the gas vibrates, which could cause this thing to actually explode if you get it too high. So things tend to go faster. The atoms start to move faster, vibrate faster, the more heat that you add to it. When you have two bodies that interact with one another, and one is carrying more heat than the next, then what's going to happen is that you're going to get thermal energy transfer. You're going to be moving the heat that's in the warmer object to the cooler object. So when you come into a classroom and you sit down on your seat, the first thing you might notice is, hey, my seat's cold. Well, that's because your tush is hotter than the seat. And if your tush is hotter than the seat, what's going to happen is your body's going to start giving up its thermal energy. It starts giving it up to the heat. And you'll notice after you've been sitting for a long time in that seat that the seat becomes the same temperature as your body. This is what happens when you have these two matching temperatures. It's called equilibrium. And right now, even this room's actually kind of warm today. My office is a little warm today. I want to open my window, but it's letting in too much pollen, so I have to deal with warm. The room is actually still cooler. It's probably right around 68, 69 degrees Fahrenheit. But it's cooler than my body temperature, which means right now, as I'm sitting here in my room, my body's giving off heat into the room, trying to make the heat the same temperature as my body. So, what's going to go on is that anything that's hot is going to move that heat from the hot side to the cold side. Okay, so there's three ways that we can move that energy from one place to the next. First of all, there's called conduction. That's, You've probably done this before. You had something that was hot, and you like a piece of metal, and the heat from the fire starts to heat up that metal. And what will happen is that when you're touching that metal, you're basically allowing heat to go from that metal into your hand. So by touching the actual object, two objects touching each other is a way of conducting heat. It works with electricity too. When you have two wires that are just not touching, there's nothing that's going to happen with the electricity. It's not until those two wires touch or conduct electricity that is actually able to happen. Convection is movement of a heat through a fluid. This is best shown if you're cooking noodles or something like that, some spaghetti or some macaroni and cheese or something like that. The first thing you have to do is boil the water. What's going to happen is the bottom of the pan gets hot first. It takes that hot water and it moves it through the water, that fluid nature of the water, to the top of the water, and that cool water gets pushed down. So hot water goes up, cool water goes down, and what we're doing is we're mixing around that hot water. Now, air is a fluid too. So when we're talking about convection and we're talking about water, air is acting the same way as water. And this is a very, 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 very important concept, is that when you have hot air rises. When you have cold air sinks. This is the difference, and we're going to talk about this a little bit later. What is high pressure? What is low pressure? Well, high pressure is when air is pushing down on you because the air is convecting down. The cool air is pushing down on you, so you're under high pressure. When you're under low pressure, the air is rising, which means it's probably going to be warmer air, and that warmer air is lifting. But that's a conversation for another day. We'll get to that a little later. The last form of energy transfer is through something called radiation, and we talked about this in the last time. There's all different forms of radiation. You have X-rays, gamma rays, those dangerous ones. You have visible light, you have radio waves, you have television waves. All those forms of radiation, the one thing that's different about these is that they are the only ones that can travel through space. So we're not touching the sun, so we can't get heat from the sun by touching, because, well, that would be bad. There's no convection going on because there's no fluids between the Earth and the sun. So the only way that we're getting energy from the sun is through the form of waves. So you guys remember the lava lamp I like to keep in my classroom? I found this little GIF of a lava lamp, and really what's kind of beautiful about the lava lamp is that it shows everything that you need to know about convection, conduction, and radiation. It starts off with the light bulb. The light bulb you can't see in this picture. The light bulb below is the radiation. The radiation from the light actually heats up the bottom glass. In fact, if you look in the bottom of a lava lamp, you'll find that there's a little bitty coil of wire, that the light is going into that coil of wire, heating it up, and that heats the lava up, causing the lava to go up. So what are some of the things you need to know about radiation? Radiation is going to be an important part of our conversation today, and next time as well. The first thing you need to know is that all objects emit some sort of radiant energy. Even though we talk about heat as being thermal energy actually lies on the electromagnetic spectrum. The electromagnetic spectrum, remember, this is the visible part of it right here. Heat would lie just right off of the red right here. That would be called infrared. So right now my body is giving off radiation in the form of heat. It would be called infrared radiation. The hotter the object radiates, the more total energy it has. So the hotter you have something, the more radiation is giving off. And this last point right here, the hotter an object is, the shorter the wavelength. So over here we have this metal bar being heated up by this flame. And you'll notice that as the metal bar gets hot, it starts off as just the color of the metal bar. This is called a black body object. Any object that when it doesn't have any heat in it, you can't see it normally. But just like the burner on your stove, as soon as you turn the stove on, you can start to feel the heat without it starting to glow. When you start to feel that heat, that means it's giving off infrared radiation. As it gets hotter, what happens is the size of the wavelengths. Look at this. You can see over here in the red size, the wavelengths are kind of large, and they get smaller and smaller and smaller as we move towards the purple. So as we go from that infrared radiation, which are large wavelengths, as we get hotter and hotter and hotter, what happens is the object will start to emit lower wavelength radiations. So as we heat this bar up, it goes from being infrared radiation to red, to orange, to yellow. Infrared, red, to orange, to yellow. And we start moving up the hotter it gets. And this is so important to everything we're doing from here to the end of the year, is recognizing that the hotter an object is dependent on what color it's emitting, what color light it's emitting. When we talk about stars and how hot stars are, we're going to be talking about how hot they are by looking at them and seeing what color that star is. What's going to happen now if you get this bar hotter than yellow? We start to mix all of these colors together. When we mix all these colors together, then that is that's considered all the colors together. We can mix all the colors of lights together. We call that white light. So when you see white light, really you're not seeing white light. You're just seeing all the colors mixed together. The last thing you need to know about them is that objects that are good absorbers of energy are also good emitters as well. I told you in the last slide I was going to show you this picture again. Here's a picture I have hanging. No, I don't hang my clothes out usually. I did this for just this video, so I'm not that neighbor. But here I've got a couple of shirts that are hanging outside of my house, a black shirt and a white shirt. And you can see it's a nice sunshiny day. Turns out that white light, basically what you're seeing when you see white light is all the colors of light being reflected off that shirt. When you're looking at a black shirt, you're not reflecting black, because black technically is not light. Light is not, that's not a color. So what you're seeing when you're seeing black is the absence of light, which means this black shirt is absorbing all the colors of light that are coming from the sun. The white shirt is reflecting it. Now you can't destroy energy, so it's not like my black shirt's turning into a battery, and it's not like it's destroying all the sunlight. What it's doing is it's changing the wavelength of sunlight from visible light to infrared light. And remember, infrared light is heat. So actually I have that thermal camera. I'll show you guys my little thermal camera I can hook up to my phone at school. And with that thermal camera, I took a picture of those same two shirts. And what you will see is that the white shirt is greens and blues, which means that is cool colors. Okay, so this white shirt's not going to be very hot. The black shirt, on the other hand, you can see that that's reds and oranges and almost going into whites, which means it's really hot. There's like a 20-degree difference in temperature between the white shirt and the black shirt. So think about that on a nice sunshiny day, you want to wear that black shirt. Well, that black shirt on a hot sunny day is absorbing solar radiation and turning it into heat. The white shirt is going to keep you cooler because it's going to be reflecting that radiation. It's not a good absorber of heat. All right, when we talk about the paths of incoming solar radiation, there's three things you need to know about that. When you go into a room, and I'm going to tell my lights to turn off for a moment. Alexa, turn off office lights. Yep, I'm a big geek. All right, so it's going to turn off the office lights. And it's going to get dark in here. How am I going to get a little less dark? I'm just going to open my window just a little bit. And just when I crack my window a little bit, the entire room lights up. Now, the thing about light is that when light is traveling, it can only go in a straight line. So light only travels in a straight line. So here you can see light coming into this room. Most of the light's going forward. But all those little particles of dust, even the dust that you can't see with your eyes, is going to scatter that light. So just the fact that there's air and dust in my room, I open my light and my window just a crack, and there's enough sunlight to go through and do my whole room. Now there's a thing I want to show you guys. This is a laser pointer. This is a little thing that I like to drive my dog crazy with. That's the only reason I have one of these at home. Of course I use those at school all the time. But if I point this laser pointer, I've got it pressed right now, and right now nothing's happening. Okay? So lasers, they only go in a straight line. Now what I've got right here is a box of matches. And I'm going to strike these matches. Now how am I going to do that? Whew. Ember went flying off and hit my pants. I'm going to turn this light on right above this, and when I blow the matches out, it's going to produce a lot of smoke. So when I produce a lot of smoke, you're going to be able to see the path of the light. Typically, you can't see that light. Hopefully, you guys will be able to see that. Typically, you can't see a laser light unless there's some sort of smoke scattering through it. That's really important. If you've ever been to a concert or a laser show, when you see something like this, before they start turning those laser lights on, this would be the boringest light show ever if they didn't put smoke, stage smoke, into the air first to scatter that light. And sunlight behaves the same way. If there was no air to scatter it, it would just be reflected right off. Then there's reflecting. 30% of all the light that's reflected off of the Earth, which means only 30% of the light that hits the Earth is bounced back. But we can still use that 30%. The Earth is pretty bright when you go to the moon. However, some surfaces are more reflective than others. I love this picture because this is a picture I took when I was in Iceland, so it was a wonderful time in my life. But I was in a helicopter and we flew across these lava fields and these ice fields. And what you're looking at right here is a whole bunch of ice. This is all ice, all as far as you can see. This is a glacier that's emptying into this valley. And as that glacier melts, you can see there's a little river. And it's on top of this black rock. And what's happening here is, in this case, here you've got a white surface, and that's reflecting a lot of light. We call that albedo. And the higher the albedo, that means the more light that's being reflected. The black rock, on the other hand, has a low albedo, which means it's not reflecting the light. What it's actually doing is absorbing that light. Absorption is where you take some objects, has the ability to take in that radiation and change and redirect that, re-emit that wavelength as a different type of energy, thermal energy. And we kind of saw that with the shirts. But once again, I went outside on a nice sunny day and I took a picture of my street. And you can actually look at this and see, look at this house right here. This house is giving off a lot of infrared radiation. This car is giving off a lot of radiation. If you look off to the sides of the grasses and stuff like that, those parts are green, almost blue, and then you have the street itself. The street itself is actually kind of red. So I'll show you what the real picture looks like. This is what a real picture actually looks at it. Why was this car so red? Well, this car's black and it's absorbing radiation from the sun and turning it into heat. This happens to be my son's car, and I kind of feel bad for him because when summer gets here, he is going to be frying. Every time he gets in that car on a hot sunny day, he's going to be frying. But you've probably had this problem before where if you tried to walk out in the middle of this black top pavement and your bare feet, you've burned the bottom of your feet. You've ran to the grass where it's cooler. And that's because the grass is a little bit more effective at throwing the light back out. Down in places like California, they're aware of this problem, and they know that all this blacktop road creates so much heat, it actually heats the entire city up. So they've actually taken to, in some areas, painting the roads white so that it reflects the light. All right, that's it for this lesson. I told you we're going to make these a little bit shorter. Next time I talk to you guys, we'll be talking about how this different types of thermal heating will affect the weather. And I look at this picture right here. This picture becomes so important. Here you are at the beach. If you can imagine, behind the camera there is a ocean. This could be like ocean shores. And look at all those people flying kites. And what I want you guys to really notice also is way inland, all these clouds. So we'll talk more about what does this differential heating, this heating at different rates, how does that affect weather on Earth? Till then, love you guys. We'll see you guys next video. Take care.